I am Debjyoti Kaur, a PhD student here at IISc, and we have an exciting series of talks lined up for today. And our first session is going to be centered on the theme of geometric packing. And our first speaker is Andreas Wiese, who is currently a professor at TU Munich. Prior to this, he was a faculty at Universidad de Chile in Santiago, and then at Vrije University in Amsterdam. He obtained his PhD from TU Berlin and followed it with postdocs from La Sapienza University in Rome and MPI Informatik Saarbrücken. And he primarily works in combinatorial optimization. And I should also mention that he was the one with whom I had my first ever publication. So it's a great thing to have you here. So today,
this is my first slide.
Oh, okay. So
You
he's,
like it?
yeah, it's awesome.
Thank you.
Yeah, very informative. So yeah.
I will say a few more words about it.
Yeah. So he's going to talk about approximation algorithms on packing problems in general. So over to you.
All right. Thank you very much. Thank you very much for the introduction, and thank you very much for the invitation. I would like to thank all the local organizers for putting together this very nice workshop that we are attending here. So in my presentation, I'm going to talk about packing problems, and actually the good thing when I talk about packing problems is that I claim actually many of you solved the packing problem very recently, and the input of this packing problem that you solve consists of your suitcase and a set of items that you might have taken with you on your trip. And the goal that you solved here is you selected a subset of the items with the hard constraint that these items must fit into your suitcase, and the objective is to maximize the total utility of the items that you take with you on your trip here to Bangalore. So for example, you probably left at home this very thick jacket here, given that we have these very nice temperatures here. You might regret that you didn't bring your umbrella because tomorrow it's going to rain, but other than that, you optimize the utility of these items that you picked. So how can you model this problem formally mathematically? Well, one very simple model is to say, let me introduce one-dimensional item for every item that you could take with you on your trip. So the heights of these bars here denote the sizes of these items. And let me introduce a one-dimensional container there on the right, where the size of this container corresponds to the capacity of your suitcase, for example, the volume of your suitcase. And then every item has a certain profit associated to it that I put here in euros. And now what you want to do is you want to select a subset of these items that together must fit into our container, so their total size must be at most the capacity of the container. And we want to maximize our total profit, which is 9 euros for this solution. But if we additionally take this orange item, we get a profit of 12 euros. Now, this problem is very well studied. It's called the Knapsack problem in the literature. Can you maybe raise your hand if you've seen the Knapsack problem before? Yeah, that's what I thought. Many of you, excellent. And good. So how can we solve this Knapsack problem? Well, there's one algorithm that maybe the very, very first algorithm one might come up with is, it's a packing problem. And packing problems actually arise in many different settings, not just when you pack your suitcase. They appear in logistics, for example, when you pack cargo on a ship, like containers on a ship, or cargo into a truck. But also in like more abstract settings, when you think of server management, when you think of assigning virtual servers to real servers, then you must make sure that the real server has enough like CPUs, GPUs, and memory for the virtual machines that you want to assign on this server. Also, in a certain sense, more abstractly in throughput maximization, if you want to select transmissions that are most beneficial for you, that can be supported by your network. And actually, whenever limited resources play a role, like limited amount of energy or budget constraints. Now, let's get back to the Knapsack problem. If you want to solve it algorithmically, the maybe very first idea that could come to your mind is just to say, let me try all possibilities. Algorithm 1. So the good thing about this algorithm is it definitely finds the optimal solution for you. However, it's of course very inefficient because the running time you need is going to be 2 to the n if n is the number of items that you have in your input. So therefore we have to be more clever. And one way to be more clever is to say, let us sort these items by their ratios of their profit divided by their size, because an item is good for us if it gives us a lot of profit and has small size. And then let's select the items greedily in this order. Like for this example, this would be this order here. So we go from left to right and pick these items greedily and add them to our knapsack until the next item doesn't fit. Good. So this algorithm is already like much faster than the algorithm from before. It takes n log n time, which is dominated, the running time is dominated by just sorting the items. However, it's not clear whether the solution that we're going to get is actually a good solution, and therefore it's not clear whether this algorithm is actually a good algorithm. So I have to specify what we mean now by a good solution and by a good algorithm. So for a problem like the knapsack problem, like NP-hard optimization problem, the ideal algorithm would be an algorithm that is fast and that gives us always the 100% optimal solution. And now since this problem is NP-hard, we cannot hope to find like an algorithm that probably has these two features, so therefore we have to compromise. And one reasonable way to compromise, in my opinion, is to say, let's still insist on the algorithm being fast, because the algorithm is slow, like 2 to the n, that's not good for us. But let's compromise on these 100%. Let's say we're happy if we might not always achieve 100% of the optimal profit, but let's say at least 95%. And algorithms that do this are exactly the approximation algorithms that I want to talk about in this presentation. Let me be a bit more precise here. So with fast, I mean that the running time is bounded by a polynomial, so it's from n to the k for some constant k. And with this 95%, I mean that the algorithm comes with a guarantee, or like a guarantee provided by the designer of the algorithm, that guarantees us that we achieve at least an alpha fraction of the optimal profit for some value alpha. So we could think of alpha as being this 95%. And I would like to insist that this has to be a worst case guarantee. So it has to be true for any possible input instance, not just for some or many of them, but really for every possible instance. And if we have such a guarantee of alpha, we said that this is a 1 divided by alpha approximation algorithm. So for example, if you have a guarantee of 50%, then this would be a 2 approximation. Now, let's get back to this algorithm here. Is this a good approximation algorithm? Turns out it's not. Because since this has to be a worst case guarantee, what can happen to us is that we get the following instance. We get an instance where there's one item that is very small, has a size of delta for some very small value delta, but a profit of 2 delta. And then there's another item that has size 1 and has a profit of 1. And then in this greedy ordering, they come in this order. And then our algorithm picks the red item and then sees that the green item doesn't fit and outputs only the red item with this very, very little profit. Whereas the optimal solution, of course, just picks the green item here. So therefore, this approximation ratio, so this ratio 1 divided by alpha, is unbounded here. We cannot bound it by any constant. However, you can fix this. So you can fix it by saying, let me either take only these greedy items from the algorithm before, or let me take the next subsequent item that didn't fit. So sanity check in this instance here, this would be the candidate solution 1. This green item is the candidate solution 2. If we pick the best, so in this case we find the optimal solution. How does this look in general? Let's get back to this example here. So now this yellow item here was the next item that didn't fit. And so if we try to add it to the knapsack, it would go above our capacity. However, we can argue the following. We can say, let us pretend for a moment that we can split this yellow item into 2 pieces. One piece that fills the remaining capacity and the remaining piece. Then you can show that these pieces here that are within the knapsack capacity, their total profit is at least the optimal profit, simply because you sort of pick the densest items that are available and you fill up the entire knapsack. So therefore you can say either these greedy items give you at least 1/2 of this profit, or this little piece, this artificial piece, gives you 1/2 of the profit. And if this artificial piece gives you 1/2 of the optimal profit, then, well, also the whole item, of course, has to give you at least 1/2 of the optimal profit. So therefore, if you pick the best of these 2 solutions, we get a 2 approximation. And now what you ask yourself in approximation algorithms, if you have such a guarantee, you ask yourself, can you do better? Can you maybe get a 1.9 approximation or 1.8 approximation? And in this case, turns out you can actually do very well. You can get a 1 plus epsilon approximation for any possible positive constant epsilon, so you can get 1.1, you get 1.01, you get 1.001, and so on. So therefore, this one-dimensional setting here is actually very well understood. However, when you think of actual practical packing settings, like packing containers on a ship, or cargo in a truck, or packing your suitcase, it's more complicated because there's geometry that comes into play, because your items must be non-overlapping inside of your suitcase. So therefore, let us study now the geometric version of knapsack. And formally, I want to define this as follows. Let's first start with a two-dimensional version of this. Let's say that our input items are rectangles, like you see here, and our knapsack is a square. And like before, every item has a certain profit. And like before, we have to select a subset of these items. But now we want that we also have to place them inside of the knapsack, so we can move every item freely around in the knapsack. But at the end, these items must be pairwise non-overlapping. And for the sake of our study here, I do not allow to rotate items, but you can still move them around freely. And like before, your objective is to maximize the total profit that you get. Any questions about the problem? Okay, good. So it turns out also that already this two-dimensional setting of Knapsack already has some applications. For example, if you place some advertisements on some billboard or some website. Also, if you cut out some pieces out of raw material like wood or metal. And it's also related to some problems that appear in chip design. So, how can we solve this problem? Well, I'm from Germany, and if you grow up in Germany, at some point in your life you will hear the sentence, Ordnung ist das halbe Leben. Rough translation to English would be, organization is half of the battle. And in this talk I want to argue that for the two-dimensional knapsack problem, this is actually a vast understatement, because there the truth is that organization is 1 minus epsilon of the battle for every positive constant epsilon. So, when it comes to, what do I mean by this? Well, when it comes to packing your suitcase...
It really rolls off the tongue in
Sorry?
that second. It really rolls off the tongue in that second formulation.
Yeah, I'm confused by the original version, not already like this, actually. Good. So, when it comes to packing your suitcase, I claim that there are actually like two extreme strategies. Extreme strategy one is, you're very diligent and you take your suitcase and you subdivide it into little compartments, like some for your socks and some for your shirts and some for your sunglasses. And then you put all these items into their respective containers. Extreme strategy two is, you just throw everything into your suitcase. Now I guess like every single one of us is somewhere on the spectrum between these two extremes. What I want to argue in this talk is I want to argue that this first method is provably mathematically a good strategy to pack your suitcase. And the second one, I don't know how to prove anything about that. Good. What do I mean by this? So first let's focus on the setting where we have squares instead of like rectangles. And what I'm looking for now is I'm looking for a packing that is structured in the following way. I want it to be structured such that the knapsack is subdivided into boxes, like these boxes you see behind me, such that in every box you either have one single item, so imagining of this as one very big item, or you have lots of items that are stacked horizontally next to each other, or you have items that are stacked vertically on top of each other, or you have items that are very small compared to the size of the box. It has been shown that there is always a packing with a constant number of these boxes and a packing of this kind that gives you an approximation ratio of 1 plus epsilon. So the optimal solution, from all we know, might be highly unstructured, but this result shows that there's always one very structured packing that is near optimal, meaning it gives you an approximation ratio of 1 plus epsilon. And throughout this talk, whenever you see an epsilon, epsilon stands for like an arbitrary small positive constant that you can choose. Good. So now once you have the structural result in place, you can use the following algorithm. First step is you guess these boxes from this structured packing, meaning you enumerate all possibilities how they can look like. And here it's convenient that there are only constantly many, because then there are only a polynomial number of possibilities how they all can look like together. Second, so for example, you like one step in this enumeration is guessing this optimal packing, this packing from the structural inside. And then the second step is you add these items into the boxes. And here the idea is that you order the items, for example, decreasingly by height, by size, but it doesn't really matter. And you go through these items one by one, and one by one you decide whether you want to select the item, and if yes, into which box you put it. So for example, you could start off by deciding for the first big item to put it into this box here, then you decide for this item that you don't want to select it. Then for this item here, you decide to select it and put it into this box up there. Then the next item you select and put here, and so on. Good. So this is like a high-level idea. This is not yet an algorithm, because it's not clear how to decide for an item whether you should pick it or not. Yeah?
Okay, so when you say odd one boxes, does it depend on the number of squares that you need to pack?
No, but it depends on epsilon. But the important point is it's a constant for every fixed epsilon, but it doesn't depend on the size of the input. And this is really important.
It's a polynomial dependence, or what's the dependence on epsilon?
It's exponential. It's something like 1 by epsilon to the 1 by epsilon. I'm going to come to this part later. Yeah. But the important point is for every constant epsilon, it's a constant. All right. Good. So this is not yet an algorithm because we still don't know how to decide for an item whether we want to select it or not. However, turns out you can figure this out very nicely with a dynamic program. Because imagine that you're right here in this sequence, already decide for all items up to here whether you want to select them or not. And now this is the next item you want to select, and you still have to decide whether you select this for all the items. For this item, it's all the items on the right, whether you want to select them or not. In order to solve this solution, the subproblem, you have to describe what you did before with the other items, and it turns out you can describe this very compactly. Because for every box that is there to hold a big item, it's enough if you specify whether it's still free or whether it's already filled. So there's two options, 0, 1. And for these vertical boxes where you want to stack items vertically, the only thing you would need to remember is the total height that is still available to you, because you stack these items on top of each other. And for these boxes where you want to stack items next to each other, all you need to remember is you need to remember the total width that is still available to you. And for these small items, like boxes for small items, turns out it's sufficient if you remember the total remaining free area up to some error of 1 plus epsilon. And now the good thing is, in order to remember this, for every single box is sufficient if you remember one single number. Yeah?
So for this free area also you probably need to do some bucketing.
I'm sorry?
So when you store this free area,
Yeah.
when you store this free length,
Yeah.
vertical length and horizontal length,
Yeah.
you also need to perhaps bucket that as you do in 1D knapsack? Or?
Actually, no, it's one single number. The number encodes the total width that you can still use. Okay. And then what happens, and now it's again convenient that we have a constant number of boxes, because then if for every box you need to remember one single number, in total there's only a polynomial number of possibilities for all these values. So therefore you can set up some dynamic program that solves this problem of adding these items into the boxes in polynomial time. So I'm happy to admit that I'm speaking many technical details under the rug here, but the important point is that for every single box you need to remember, it's only one single number matters, so therefore there's only a polynomial number of possibility of combinations overall. Good. So then this gives you a 1 plus epsilon approximation algorithm in polynomial time, as shown by Janssen and Solis-Ober. I would like to mention that if you read the paper, it's not written from this viewpoint here, so now I'm looking at their result from a slightly different angle, but conceptually this is exactly what they're doing in the paper. Good.
And the order in
Yeah.
which you process the squares, it doesn't matter.
Doesn't matter at all.
There's no density constraint.
No, not at all. Yeah. You can take any order that you like. Yeah.
And so DP in some sense, it's not a configuration LP, but
No.
it's just a DP over the possible arrangement.
Exactly, it's a dynamic program. It's now linear programming involved at all. Yeah.
This initial partition that you are getting, this is coming from the DP, or like
Which initial
the
part?
initial partition where you decide now?
You mean this enumerate? Yeah, okay. So for these boxes, you enumerate all possibilities. So the thing is, like for every single box, there's a polynomial number of options where it can be placed.
And
In
because
the-
they're constant, that's why it is still constant.
Exactly, you have a constant number of boxes, right? Yeah. So there's like two parts where you need that you have a constant number of boxes. First one is exactly this, where you enumerate, and the second part is the dynamic program. More questions? Yeah. So you mean you enumerate all possibilities. So like for every box, there's like a polynomial number of possibilities where it can be located in the knapsack, and then if you have a constant number of boxes, it's a polynomial to a constant, so again a polynomial. All right, good. So now on a high level, what we did is we start out with one two-dimensional container, and we reduce this problem to a setting with a constant number of one-dimensional containers. And this was easier to handle than one two-dimensional container. Good. So Now let's generalize the thing to rectangles rather than squares. And for when you handle rectangles by some standard reductions, you can assume that there are 4 types of different rectangles. Type 1 are rectangles that are large in both dimensions, meaning their height and their width and their height is a constant fraction of the height and the width of the knapsack. Second type are what I call horizontal here, meaning that they're wide, but they are thin. Third type, what I call vertical here, is exactly the opposite, and then there are items that are small in both dimensions compared to the size of the knapsack. So there's some constant that define these thresholds here. Now, a natural thing to do is to try the same thing. Let's say I take my knapsack here and divide it into a constant number of boxes, and then inside of each box I either place one single large item, or I place only vertical items stacked next to each other, or I place only horizontal items stacked on top of each other, or I place only small items. And it has been shown that if you insist on having a packing of this kind, there is always a packing that uses only a constant number of boxes and gives you an approximation ratio of 2 plus epsilon. And then the algorithm is pretty much the same algorithm as before. Step 1 is, again, you guess these boxes, meaning you enumerate all possibilities, you convince yourself that there's only a polynomial number of options for those. And for each option, you add these items into the boxes with pretty much the same dynamic program as before. And then this gives you a 2 plus epsilon approximation algorithm in polynomial time, as shown by Janssen and Sai. Now, this approximation ratio is, say, only 2 plus epsilon, and the natural question is whether you can improve it to, for example, 1.9, or maybe even all the way down to 1 plus epsilon. Turns out, if you think a little bit about it, you realize that this factor comes solely from this structural result in orange on the top. So for example, if you were able to prove that there's always also a structured packing with a constant number of boxes that gives an approximation ratio of 1.999, then this would immediately translate to a 1.999 approximation factor. Right. Unfortunately, we proved that this is not possible. Why is this? You can have an instance that looks like this. There are some very thin items that are stacked very tightly here at the edge of the knapsack. Then there's the second group that is much larger, whose items are also stacked here very tightly at the edge here, and then this goes on for a logarithmic number of groups. So this capital N denotes the width of the knapsack. And now the thing is, like, if you wanted to place like one box that contains all these vertical green items, you can avoid like losing all these horizontal green items, because they're kind of in the way of this box here. Similarly, if you wanted to place all the horizontal green items in a box, then you have to lose almost all these vertical green items. And now the thing is that you are only allowed to use a constant number of boxes, but you have a logarithmic number of groups. This means for pretty much every group you have to lose a factor of 2, so therefore you cannot prove a better factor than 2 in such a structural result.
But we're not confined to guess boxes. We could have guessed, instead of boxes, like in this example, L-shaped.
That's exactly what I'm going to have on the next slide. Thank you very much. No, seriously. So this is like some high-level idea, but we also make this formula that formally you cannot get better than 2 here. And now we did exactly what you suggest. Very good. So we looked at different packings that look like this one here. So again, they have boxes as you see, but also as you suggested, there's actually one container here at the edge here in orange, on here, that has the shape of an L. And this container is a bit different than the other ones because there are vertical and horizontal items together in this container, and they could interact in a possibly very complicated way here at the bend. Whereas for all the other boxes, you either have only big items, only one actually, or only horizontal items, or only vertical items, or only small items. And we proved that if you allow only one single of these L-shaped boxes, then actually you can break this barrier of 2, and we show that if you use a constant number of boxes like the ones from before and one L-shaped box or container if you want, then you can get an approximation ratio of 1.89 plus epsilon. And then the corresponding algorithm again first guesses these boxes, including this L-shaped container, and then adds the items to the boxes. However, now this algorithm is more complicated because here at this bend, since the horizontal and vertical items they could interact in a complicated way with each other, we need a more sophisticated algorithm. Turns out you can also set up a dynamic program that can handle one of these L shapes here. And if you put this together, this gives us you 1.89 plus epsilon approximation algorithm. So now we use a constant number of boxes and one single L-shaped container, and then the natural question to ask is like, can you maybe do better if you allow like maybe more L-shaped containers, or maybe more different kind of containers like U-shaped containers or Z-shaped containers? And turns out, yes, you can do this. So we prove, and then what we'll do is, in the vertical parts of these containers, we'll place only vertical items. In the horizontal parts of the containers, we'll place only horizontal items. And again, there are some boxes that have only has one single big item, and then there are some boxes with small items. And turns out then you can actually do even better. Then if you can use a constant number of boxes with an L and U and Z shaped containers, then you can bring down the approximation ratio down to 4/3 plus epsilon. And the algorithm for this is, again, you guess these boxes, enumerate all possibilities, and then you add the items to the boxes. But now it's even more complicated, because before there was one single L shape, one single bend where horizontal and vertical items interacted. And now they interact in every single one of these bends. Now these bends are only constantly many, but still, because of this, the dynamic programmer that you used before no longer works. It even already fails if you have two L shapes instead of one. So therefore here we use a very different algorithm that finds a near optimal way to pack the items to the boxes. And then this gave us a 4/3 plus epsilon approximation algorithm now in pseudo-polynomial time, so n is the width and height of the knapsack. I'd like to mention that the pseudo-polynomial time running time only comes from our algorithm. It's not doesn't come from the structural results. So from all we know, there could be maybe a different algorithm that runs in polynomial time and achieves the same guarantee. Now, if you, yeah, please.
Adding every L, U or Z, like, increase the dimension in the DP, make it, like, how complex does this make the dynamic programming?
I mean, the exponent of n here depends on the complexity of these boxes. So if you have a constant number of these boxes, this constant will affect the exponent of the running time. I'd like to mention that also we also use like a bit more complicated shapes that are like generalized Z shapes and U shapes in a way. The definition is a little technical, but we make sure that we have a constant number of these corridor pieces overall.
But the choice of these structures like L, U or Z is guided by the analytics in the sense that these are shapes for which you can do a near optimal.
Yeah, there's an interesting trade-off. On the one hand, you want to have shapes that are complicated enough that you can prove that there's you get a good approximation ratio. At the other hand, they shouldn't be too complicated because you still need an algorithm that packs the items like near optimally into them. So there's had to strike some balance here. There was another, yeah.
Is there any stronger hardness of approximation results if you allow arbitrary orientations?
Like rotations or arbitrary containers?
No, like rotate.
Not that I'm aware of. I mean, like also here we don't know the precisely best approximation ratio. I mean, here I'm gonna come to this in a second, but I mean, rotation is a different game, I would say. Yeah. Okay, good. So now, when we start with boxes, and then okay, boxes are not good enough, so let's allow more complicated containers. Yeah.
Sorry, could you please repeat what n was? Capital N.
Capital N is the width of the knapsack. Okay. So we started off with boxes and said, okay, boxes are not good enough, so let's allow more complicated shapes and to get a better approximation ratio. But you will also turn this around and say, like, if you want to have an approximation ratio of 1 plus epsilon, how many boxes do I need? And it turns out that you do not even need that many boxes, because we proved that if you want to have an approximation ratio of 1 plus epsilon, then the polylogarithmic number of boxes is actually sufficient. And also this gives you an algorithm. You could say, again, you guess these boxes, add the items to the boxes. Then this gives you a 1 plus epsilon approximation algorithm in quasi-polynomial running time, assuming that n is bounded by some polynomial or even quasi-polynomial function. Yeah, so in particular, this gives us some sort of indicator that 1 plus epsilon should be the right answer, at least assuming that the input data are polynomially bounded. Good. So, now we talk a lot about like squares and rectangles. Yeah, good. You have a question. Good.
How does that bound is relative to the earlier 2 plus epsilon bound that you showed through the log n boxes? How does this?
Yeah, good. So in this lower bound where I said we need at least, you cannot beat factor 2, is that we had like this logarithmic number of groups. And now I allow you more boxes, like I allow you even a fully logarithmic number of groups. So what you could do, for example, you could say for every single group you make, 1 by epsilon boxes or something. Yeah, so like, the actual lower bound of like this bound of 2 is a bit more subtle if you look into the details, but it turns out that if you allow a logarithmic number of boxes, then this no longer holds. Okay. More questions about squares and rectangles? Yeah.
So in your previous slide you were allowing use shape also the Z shape.
Yeah.
Is there any restriction why you don't go for also like a rectangular box with a rectangle on the side?
Rectangular box is like the box we used before. Like some sort of spiral.
Yeah.
Yeah, we can also handle this. It's like the thing is like the precise definition by kind of corridors we handle is a little technical, but like if you have spirals, those we can handle as well. Yeah.
But they're also the bound of the same approximation factor holds that if you want constant number of boxes, then the same approximation factor.
Yeah. So what to be precise is we get the same ratio that you can achieve for these kind of boxes that you pick. If you say, for my instances, if I allow only spirals, this is good enough to get 1 plus epsilon, then our algorithm is going to give you 1 plus epsilon. Okay.
So here it's pseudo-polynomial because of capital N, right?
Yeah. So little n is the number of items. That's you have at least n bits in the input, but capital N you can encode in log n bits, so it's not polynomial.
So is there any hardness that you can't get away from pseudo-polynomial if you...
Not that I'm not aware of. For all we know, there could be one. There's a different problem called strip hacking, where there is actually such a distinction between pseudo-polynomial and polynomial, but here, I don't know. Yeah.
Sorry, so in general, if you have these thin pieces, and I don't know the actual definition of them, do we know how to pack them into general orthogonal polygons?
What do you mean by thick pieces?
Thin pieces.
Thin
like
pieces.
the
Yeah, these vertical ones, yeah. Good, yeah.
So I'm assuming that for the Z's and the U's and all that, the complexity probably comes from the fact that you don't know how to pack them well, like these thin pieces.
Yeah, that's right. If you have a Z-shaped container, it's not obvious at all how to put items into it because you have these interactions at the bends that make your life hard. Alright, so now we talk about like squares and rectangles. Now I claim that there's also another very natural...
One question.
Yeah, sure.
So the polylog structural result, not a computational one, just the first bullet that you had in the previous slide, is that right? So yeah, I'm just asking the fact that there are polylog many boxes that you need to sort of...
Oh, I see. Not the...
As a counting question.
So the precise polylog function we have here, I would doubt that it's precisely timed. Maybe you can improve the exponents. But if you wanted to try some lower ones, I think the first thing to check is like this instance for this factor 2 bound. So for example, I would doubt that you can get like log, because there you have a logarithmic number of
Small of log n is not possible.
little of log n. Oh, I see. Yeah. Good. All right. Good. So now after talking about squares and rectangles, I claim that there's also another very natural class of geometric objects that is worth studying here, which are circles. Why circles? Well, I claim that in this world there are actually many important objects that have the shape of a circle. For example, pizza, or cakes, or naan bread, and also many Indian desserts have the shape of a circle. And last but not least, also the world itself has the shape of a circle. And actually, it's not a surprise that you see all these like delicious food here, because as you might know, there's actually a proof that circular foods are the best, which was published in the international journal taste.com.au. So, how can we pack this yummy food? Well, let me again distinguish the object into large and small like before. So I say a circle is large if its radius is at least a constant fraction of the width of the knapsack. And let's say a circle is small otherwise. So there's some threshold for the two. Now what happens is that circles are related to squares in a way, like both are fat objects. And for example, one consequence is that they have some things in common. For example, if you have squares, you can say if you have only large squares, you can have only a constant number of them in any feasible solution, and in particular in the optimal solution. Simply because every large square uses up a constant fraction of the area of the knapsack, so therefore you can have only constantly many. And this is useful because you can enumerate nicely, for example, the large squares of the optimal solution. And exactly the same thing is true for large circles. Also, again, there can be only a constant number of them in the optimal solution. However, and there's also, for example, there's some other geometric problems like independent set of objects, for example, where there's an algorithm for squares that translates directly to circles, actually without any major modifications. However, in our setting, some things are a little different because if you have squares, if you have small squares, then you can actually fill the area of the knapsack almost perfectly up to some part of at the boundary. And this is nice because then you can use area arguments. You can say something like, in my algorithm, I select small squares, whose total area is at most the area of the knapsack, and then you will know that you can pack them almost perfectly. Thanks to this, because you can fill the area almost entirely. Unfortunately, this is not true for circles, because for circles you always have these like wasted space here when you pack, let's say, like in this example, circles of the same size, so we can no longer use these useful area arguments. Another thing that is different is that for squares, you can always assume that there's a solution, like an optimal solution, where everything is like flush to the bottom and flush to the left. And then you can show there's always a square that sits in the bottom left corner, and the other squares are tightly packed with each other, flush to the bottom and left. And one consequence is, for example, is that there's always a solution with only integral coordinates, assuming that the heights and the width, the size of the squares, height tends to equal width, is always an integer. So this is good. For circles, however, this is not the case, because it could be that the optimal solution looks like this. It's very tightly packed. You cannot flush this to the bottom left. And even for circles, it's not even clear that there is always an optimal solution where the centers always sit in integral coordinates or even in rational coordinates. From all we know, it could be that there's a set of circles that have integer radii, but you need irrational coordinates. So what do we do about this? So our algorithm for circles, we first guess the large circles, meaning we guess their identities, we guess who they are. And then we guess their placement, but only approximately, because of this problem that we don't even know whether rational coordinates are sufficient, and even if yes, whether how many bits you would need. So what we do is, like for every large circle, we guess a box, like it's very small, and we guess that its center must be contained in this box. After guessing this, we need to verify that this is actually valid, whether it's actually possible to put these circles into these boxes such that the circles don't overlap. So we need to verify this, and we do this with a system of a constant number of variables and a constant number of polynomial constraints. How do we do this? Well, we say for every circle, there is a center that we can express by two coordinates, horizontal and vertical. And we add a constraint that says that this center is inside of the box. Similarly, let's say we have a second circle, its center I call C2. We express a constraint constraints that make sure that its center is in this guess box for the second circle. And then if you want to express that these circles don't overlap, what we say is we take their radii, R1 and R2, and write down a condition that says that the distance of C1 and C2 is at least R1 and R1 plus R2. And if you square both sides, you get a polynomial inequality. And then we use a result that's actually a very big hammer that says that you can decide in polynomial time whether such a system is feasible, whether it admits a solution. This big hammer might not give you the actual solution because sometimes these systems have only a rational solution, so then you could not hope to get it in polynomial time. But it can say yes or no, and the answer is going to be correct. So this is what we do. And then we place a grid. We want to continue with the small circles. So what we do is we place a grid here. Yeah.
That would say it might be rational but algebraic still, because you have got.
Yeah, right. It could be yeah. But from all we know, it might be irrational. Yeah. Okay, good. So now we want to pack the small circles, and in order to do this, we place a grid. And let me zoom into the grid a little bit. So what happens here is that there are some grid cells like this one here that is completely covered by one of the gas large circles in our solution as well as in the optimal solution. So we of course cannot use it, but that's okay. The optimal solution cannot do this either. There are some cells like this one here that is not covered at all, not even partially by any circle in the optimal solution, also not by any circle that we put. So therefore we can use it entirely. Then there are some cells that are not so great. There are cells like here at the boundary, they are partially overlapped. And from all we know, we don't even know how exactly they are overlapped because we don't know the precise placement of the center. So they are not so great. So these are marked here in blue. And these I say I don't want to use. I want to be on the safe side. I say I don't want to use them. Now there's a risk. And the risk is that I waste space due to this, that the optimal solution could use to pack very profitable small squares. However, it turns out that this is not so bad because since our circles are circles and they're big, you will always find some cells here at the corner that for sure not touched by any big circle. And if you calibrate the size of the grid correctly, then it turns out that these blue cells that you lose are actually very small, very few compared to these white grid cells you're going to find for sure here at the corner. So therefore you can afford to lose these blue grid cells. Now let's look more into the white grid cells we can use. So they are in the optimal solution. They could be partially used. They could be used by the circles from the optimal solution. So next thing I do is I don't like that some of them overlap the boundary. So therefore I temporarily remove all the ones from the boundary, and the intuition is that there are only very few. Their total area is very small because the circles are so small. So therefore, intuitively, you can afford this with some technical tricks. Secondly, I look at every single grid cell, and with some random shift, I delete some of the circles in this grid cell so that I can push everything towards the center. And the effect is that then the remaining circles are still very profitable, almost as profitable as the original ones. But they fit now into a smaller grid cell. They fit into a cell that is by a factor of 1 minus epsilon smaller than the original one. And this is good. So on a high level, what we did is we started with one two-dimensional container and reduced the problem to a constant number of two-dimensional containers. And now this doesn't look like an improvement at all, but the important point is that in these constant number of two-dimensional containers, we have resource augmentation, meaning that we can use the entire grid cell and compare ourselves to a grid cell that is actually smaller. And this is good. And then what we do is we continue recursively on the constant of grid cells with resource augmentation. And so I'm not going to go into details here, it's also technically quite involved. But the important point is that since we have resource augmentation available, we can do things like rounding up the radii of all circles to powers of 1 plus epsilon and other things, which makes our life actually a lot easier. And if you put this together, this gives you a 1 plus epsilon approximation algorithm in polynomial time. And I would like to share with you that the same result was obtained independently by Gomes-Chagas, De La Riva, and Kelly Miyazawa, also in this year. What is this asterisk? This asterisk is there because for the large circles, we do not know their precise placement, but can only guess that it's up to this error bit of this bounding box. We also have some generalizations to pentagons and certain generalizations of those. Don't want to go into the technical definition, but this technical definition is designed such that we can still say if we have large objects like those, we're going to find this empty space here at the corner and our argumentation goes through. And if you have polygons, we even get their exact placement, so this issue with this irrational coordinates is going to go away. And also we can handle arbitrary small convex fact objects. There we use this argumentation for grid cells and the resource augmentation. And I would like to mention that for these results, the items don't have to have all the same shape. It's totally fine if the input consists of exactly these shapes that you see here on the top right. There can be triangles, pentagons, rectangles, or small aspect ratio. This all works. Good. Now, let me briefly talk about more dimensions, say 3 dimensions and more. First, the fast good news, this algorithm for circles extends to spheres in any constant dimension, 3, 4, 5 dimensions, for example, without any modifications. Now for cubes and hypercubes, There was the result for squares I mentioned before doesn't directly translate because it was redesigned for 2 dimensions. However, there's a recent improvement, and it also simplifies certain things. It has been shown that there's a Gannet packing with a constant number of boxes that gives you a factor of 1 plus epsilon, where there's very structured, meaning that every box is either looks like this in a sense, there's a grid in it, such that every grid cell contains exactly 1 square. And the second type is that intuitively, like for before these cells for small squares, meaning that there is some technical definition that makes sure that with some greedy method you can actually place these squares. And one intuitive way to think of it is that all these squares are very small compared to the size of the container, and there's some empty space in the container to account for small packing errors we still make. And then the algorithm is kind of the same as before. So the heavy lifting here is a structural result, which I find very nice indeed. And this was shown recently by Janssen, Kahn, Lira, and Srinivas. Good. So now, kind of coming back to what you asked before, if you look at this structural result, this algorithm here, it says you get a 1 plus epsilon approximation in polynomial time. And now if you look more and more into details, you see that the exponent of n actually depends on epsilon and its dependence is exponential in 1 by epsilon. So the whole running time is double exponential in 1 by epsilon. Not just for this result, actually for all results that I talked about, this was the case there's some technical reason for this, but it's the same reason for all these results. On the other hand, for one-dimensional knapsack, we now have this recent result that gives us a running time of n to the 1 by epsilon squared, up to logarithmic factors, and this is even tied under some conditional lower bounds. And as you probably know, there are also other results where people say, so for example, for problems like orthogonal vectors, for shade distance, longest common superstring, there is an order n squared algorithm and there is a conditional lower bound. And in this case says either we can solve all these problems faster than n squared or none of them. And similarly for all pair shortest path, negative triangles between a centrality, there is an order n cubed algorithm and some matching conditional lower bound. So what happens here is that in these results here, we have very moderate exponents of 2 and 3, and we have a justification for it. Whereas in our setting, we have very high exponents, and we have not even a justification for that. So therefore, we looked into this, and we proved the following. We proved that for squares and hypercubes, you can actually get a much faster running time, meaning you can get a running time of the form n times log n to some function of epsilon and d. And similarly for rectangles, you can get a 2 plus epsilon approximation algorithm, get in a running time that's of the form n times polylog n for every constant epsilon. So meaning that for every constant epsilon in d, your running time is n times polylog. So therefore, in particular, you cannot prove a lower bound of something like n to the 2 minus delta because these running times are faster for every constant epsilon in d. Let me briefly say one few words about how we do this. We again start off with these structural results from before, and we massage it a little bit such that we transform it to what we call a constant number of easily guessable boxes. What I mean by easily guessable boxes, I mean that every box has certain parameters, and all parameters you can guess very fast. There's only a logarithmic number of options apart from one parameter that here, for example, is the width of these grid cells. And then in our algorithm, we kind of mix guessing these parameters of the boxes and the items. So we first guess these parameters we can guess easily, then add the items into the boxes, and at the same time set the remaining parameters using some framework called the indirect guessing framework from some previous work. So to sum things up, we talked about geometric knapsack problem. There's now a 1 plus epsilon approximation algorithm for cubes and hypercubes that is fast. I mean, fast in a theoretical sense, n times polylog n. And for rectangles, we have a 4/3 plus epsilon polynomial time and 2 plus epsilon with this faster running time based on these structural packings. And then for spheres, we have, and small fat convex objects, we have 1 plus epsilon approximations, which is based on this recursive approach with the grid. Thank you very much for your attention.
Thanks, Andy. Are there any questions?
Do you have algorithm for mixed shapes as well, and like For example, both rectangles and circles together.
For one result, yeah. So if they are small, okay, say if there are small convex fat polygons, you get 1 plus epsilon. I think you could also add circles in this result if you wanted to make things a bit more technical, but I don't think there's a major obstacle here. For the other results, we either have squares or circles. I mean, I would guess that the result for circles you could also add squares if you wanted to. I would have to check details, but it sounds like something doable. Yeah.
So the rectangles, is there extensions to higher dimensions, cuboids?
Yeah, actually, I learned here yesterday that there's a recent improvement by Arindam and his co-authors to three-dimensional cuboids.
So there will be a poster by our chair, session chair, the poster session. Use Dr. Wood.
I guess can we take the remaining questions offline in the interest of time?
All right.
We have a small token for Andy.
Oh, thank you so much. This is great. Thank you so much.
There's a small announcement.
Yeah, as you can see, we have a packing constraint happening in the auditorium. To accommodate the registered speakers and specifically for unregistered students, we welcome you to sit in 117. The talks are being projected there, and as soon as space opens up, we'll call you back. So if you can, I think the first few sessions would be a bit more popular. So if you can give more speaks, there's some speakers and other registered participants who are waiting. So if you can accommodate and volunteer to sit in room 117, which is down the hall, that will be very helpful for us. Yeah, thanks. As soon as space opens up, we'll call you back.
here in Anders' name, Åman. This, the first two A's, that's actually an old-fashioned way to write a special Danish vowel called Å. And according to Danish alphabetic order, it should actually go to the very end of the alphabet. But Anders insists that since we are writing English papers, he has to squeeze in front of me, which I'm not so used to yet. But he says that if we one day write a Danish paper published in a Danish journal, then he will accept to go last. Okay, we just heard a lot of nice motivation for studying packing problems in Andy's talk. So here I have assembled a bit more pictures from everyday life. This is one of my friend's kitchen drawer. And here are some more. We saw some similar examples before. And we have the examples from big industries like logistics. And I think there's definitely still some work to be done in this context of logistics, because when my partner and I arrived here today at 1 a.m., our luggage didn't arrive.
Some greedy algorithm at work.
Yeah, and also in 3D printing, we have a nice three-dimensional versions of some very complicated irregular packing problems. And then what is especially important in my talk is in the context of production of clothing and furniture. So here we have something like a leather hive or a piece of fabric, and we need to cut it out into some specific pieces so that we can sew them together into clothing or furniture. And there we have a good motivation for why we study also translational packing problems. So that means that the pieces are not allowed to be rotated. Because, for instance, if you look at this jacket, you have these nice vertical stripes. And if you had been rotating your pieces arbitrarily, then you would not have such a nice design. And even if there's no obvious pattern of the fabric, you can take a look at your clothing and see that the weaving, the fabric has a direction according to how it was made, and that implies that it should. So you should have some vertical pattern on trousers, for instance, and that is often denoted with these arrows when they make arrangements for how to cut out. Then these arrows show how the piece should be placed. This is an example from industrial software for finding packings of in fabric. Then I'm going to tell you about online packing. So we have online and offline. So in Andy's talk, everything was offline. So that means that you have full information in the beginning and you can do all the computation and then make a decision. And then we are looking at strip packing. So that means that our container is a strip like this, so it's unbounded to the left, but has no boundary to the right. But we want to use as little of it as we can. And then we are looking at convex pieces, so convex polygons. We want to pack convex polygons here. And we are looking at translations only with the motivation from fabric cutting. So so that means that in the offline problem, we have some set of convex polygons here, and we want to find out how to put them in the strip, and we can compute, and then we find out, okay, we want to put them here, and then the cost here is how much of the strip we have used. Then in online, we get these one by one, and have to decide where we want to put it. So we get this one, and then we say, okay, that's nice to get it here. We don't know what we then get next. But we got this one, and then we put it here, and now this one, and put here. And then you see, in the end, we measure the cost in the same way. But then it's of course expected that we cannot do as good because we didn't know to begin with what we would get. Then similarly to the concept of approximation ratio, we define the competitive ratio here. So the competitive ratio is some constant C, which is a number at least 1. That means that the online cost, the cost we got over there, should be at most this C times the optimal offline cost. So it's how much worse our solution gets. So we can also write it like this, that the cost of our algorithm is at most C times opt.
No assumption on the arrival order.
No assumption on the arrival order. They come in arbitrary order. Yeah. And then we say that an algorithm is competitive if it satisfies this for some constant C. Yes?
In the online setting, when we are introducing a new polygon, are we allowed to change the previous polygon?
When we get a new polygon, we are not allowed to change the previous ones. We have to make a decision and then stick with it.
So do you already know the number of items that will be added?
We can assume we know the number of items. But yeah, I think it actually doesn't matter for the results I'm presenting. So then we were wondering what in this setting here, then does there exist a competitive algorithm? Is there an algorithm that places them so we get a packing that's at most a constant worse than optimal? And we show that there's no such algorithm.
So is the adversary adaptive or oblivious?
The adversary is adaptive, so in this lower bound, the adversary inspects where we put the item and then it chooses the next one in a very evil way. And then what if all the pieces are very small, so all the pieces have diameter at most delta for some small constant delta? Again, we show that even when the pieces are tiny, we still don't have a competitive algorithm. So this has a remarkable consequence.
So
Yes?
in the previous question, so are the polygons arbitrarily complex? Or,
Yeah, so the polygons are actually this lower bound here, we realize it all with parallelograms. So we don't need arbitrarily complex polygons to do this. Yeah, so it has this interesting consequence that whatever algorithm you suggest for packing polygons in this setting, then I can come up with a stream of polygons so that those polygons are tiny. They are like at most 1 millimeter on the widest dimension, and they can actually be packed inside a piece of fabric of 1 by 2 meters. But your algorithm will not succeed in packing them into a strip of 1 billion meters. And when I told this to my mom, I tried to explain her what I was doing. Then she said, "No, that can't be true. I could surely do better." We are also looking at some other versions of packing. So bin packing, there we pack into unit squares, and then the cost is how many of them we need. So this would be a packing of cost 4. And there again we show that there's no competitive algorithm for this, even when all our objects are very small.
So, like, is this just the gap because you are looking at additive approximations? Let's say there are these definitions definitions of competitive ratio that allow you to have an additive term as well, or opt is large enough. So the example, like the thing that surprised your mom, that was because of the fact that opt itself is so small, or so if I, let's say, changed my definition to have like C times opt plus, let's say, additive term D, even then this is...
Yeah, I don't think that would help, because I mean we could make it succeed any additive term as well.
Okay.
I think your question is absolute approximation or asymptotic approximation?
Yeah, exactly, yeah.
I guess that it's even a lower bound on the asymptotic competitive ratio. Then there's this version of packing. It's not so often studied. So here we are allowed to put our objects anywhere in the plane, and we want to minimize the perimeter of the bounding box. And there again we show that there's no competitive algorithm. And then we look at this version here, which I call square packing. It comes with a parameter delta, so that's it's defined so that we get a sequence of pieces that is convex polygons, and we are guaranteed that the area sum to at most delta, and also that the diameter of each of them is at most delta. So they are small, and their total area is also small. And then we want to know if we can always pack such a stream. However many there are, is it possible to pack them into a unit square if delta is just small enough? And we show that there's for no delta, there's an online algorithm that can do this.
Maybe so. I mean, these results show that online is extremely hard. But what for the offline version of let's say strip packing, what is known?
I will get to that.
Okay.
Yeah. So far in this context of online packing problems, it had only been studied how to do axis parallel rectangles, and that had been studied for a long time. So here is a paper from the 80s with a strip packing algorithm with constant competitive ratio, and then bin packing. And here is a previous paper that I did with Lorenzo, where we studied the perimeter packing, and we showed that for axis-aligned rectangles we can do a competitive algorithm, but if we want to minimize the area of the bounding box, then there was no algorithm. Then there was this square packing problem, so that's related to a peculiar theorem called the potato sack theorem. So in this fun math book, there's this corollary. It says that 1 kilogram of potatoes can be put into a finite sack. So what they proved is that if you have a collection of convex bodies and you have a bound on the total volume of them and a bound on the diameter of each of them, then they can be packed into a cube whose size depends on this volume and this bound on the diameter. And that means that, so if you have 1 kilogram of potatoes, then you have a bound on the volume because they weigh 1 kilo, and they are convex, usually at least, and you also have a bound on the diameter because potatoes are not like extremely long and skinny. So therefore, they can be packed into a cube of size bounded by the volume and the diameter, and this cube could then also be packed into some sack of bounded size. And this has also been studied in the online setting. So, but that is using rotation. So, if you have your potato here, you can rotate it like this, so the diameter is horizontal, and then you can pack it into a bounding box, and then you can pack it as a box instead of this more complicated convex polygon. In ours, our result is that there is no potato sack theorem for online packing convex polygons without rotation. Yeah, then we also look at, we don't only look at lower bounds, we also look at how you can actually make a good packing or something slightly better than the naive. So the naive algorithm just takes each object and puts it into a stream, into the strip as deep as possible. So then if we get this piece first, we would put it here. And now I have made some a tricky example for this algorithm. So if we get objects like this alternatingly, then we get a packing like this. And then the cost of the algorithm would be n times w, where w is the width of this one. And of course it would be much better to pack it like this. Here, so here the optimum is just something like 2 times w if you make the piece skinny enough. So that shows that the competitive ratio is at least n½ for this algorithm. It's actually also at most proportional to n, because you can see that the algorithm uses at most n times the maximum width, and the optimum must use at least the maximum width. You cannot pack these pieces without using as much as the widest piece. So that shows that the algorithm gives a solution which is at most n times the optimum. So then we have an upper and lower bound which is linear in n. So this algorithm is theta of n competitive. So we were wondering if we could make a better algorithm. And then we found a more complicated algorithm that has this competitive ratio. So it's n to the logarithm of 3 minus 1. The logarithm is in base 2, and then times a log factor. And this log 3 minus 2, that's 0.59. So it's better than here we have 1.0. And in the end, I hope I will have time to briefly explain you how this algorithm does, but it makes some packings that look like this, where it tries to allocate parts of the strip to pieces that have a similar slope. Before our work, there were only algorithms described for axis parallel rectangles. So what about offline? That was a question from before. For offline algorithms, there was this paper by Helmut, Mark, and Christian, where they show that if you want to pack the pieces into a minimum area bounding box, you can do that within a constant approximation factor. And the idea is that you group your objects into similar height, and then in each of these groups, you sort the pieces by the slope of this spine segment, which is the segment connecting the top point and the bottom point. And then you sort them like a fan, like this. And this gives a good way to pack these. And then you will stack strips of this on top of each other and then get a good packing. And we showed in our paper that this generalizes to the other versions of packing that we look at: strip packing and bin packing and perimeter packing. The proof that there are no competitive algorithms for the online versions of the packing problems, that actually uses that it's impossible to maintain a sorted order like this when the pieces come online. You cannot do that. And to make that formal, we introduce a new online sorting problem. So it's a problem that comes with two parameters, gamma and n. And we have an array of size gamma times n, and we need to put in n numbers in this array. And we assume there's already a 0 here left of the array and 1 here to the right of it. And yeah, gamma is this size factor, so that's how much excess room we have in our array. So it's a number which is at least 1. And then we get numbers one after the other from the unit interval. So maybe we got 0.7, and we have to choose where we want to put it in the array. Maybe we put it here, and then we got 0.2, we put it here, 0.4. And then you can see here now if I get a lot of, so the aim is that we maintain a sorted order, but then when we get a lot of zeros now, we were forced to put a 0 somewhere where it wasn't sorted anymore. Then in the end, when we got all our n numbers, we number them from 0 up to n plus 1. And then the cost is the sum of the consecutive differences in this left to right order of the numbers. So here you can see that because we have a 0 here and a 1 here, and we get numbers between 0 and 1, then the optimum cost is exactly 1. So that would be what we would get if the numbers were really sorted. But now it's difficult to, it's impossible to get that because we get them in online order. Yeah, so we study this problem, and then we see that we make a proof that if we have a delta competitive algorithm for the online sorting problem with gamma times n space, then we have this trade-off that says that then the delta times the gamma, so the competitive ratio times our space is at least log n over log n. So it means that if you want to do very well on the competitive ratio, you need some extra space. You cannot do very well on very little space. Then we also study the problem where gamma is equal to 1. So that's an interesting special case where we have exactly as much space as the numbers we get. And there we show that we have matching lower and upper bound of square root of n. And actually I gave a lecture about this in our advanced algorithms course at University of Copenhagen. And then I had prepared some spreadsheets, so the students were playing online sorting against each other. One student was the algorithm and one was the adversary. So the adversary set a number, and then the algorithm had to put it into the spreadsheet, and then they compute the cost in the end and see and find strategies. It was actually quite a fun game to play like that. And we also show that if you have a little bit extra space, then you can get a complicated competitive ratio like this. There's a big bound between the lower bound we get up here and then this upper bound, which is a nice problem.
Sorry, what's the role of gamma?
The role of gamma is to say how much extra space you have in your array. So gamma is a number at least 1, and that means that you should have that number times the n memory cells, but you are only going to use n of them.
But if there has to be like a cutoff, right? If gamma is itself n, then you can get a cost of 1.
Yes, yeah, I think you are right. If gamma is n, so you have n squared cells, you can. Yeah. Yes. Yes, so in our paper we do reductions like this. So we reduce online sorting to strip packing, and then we reduce strip packing to strip packing with small diameter, and bin packing with small diameter, and square packing. And then we reduce square packing to perimeter packing. And I would like to, there's a nice proof of this. but I actually don't think I have time. But I would love to show you offline if you are interested. So I think I will skip it in this talk. And yeah, this is also an older, so I will skip this slide. We basically just assume that we have a packing algorithm, and then we use that packing algorithm to tell us where we should put our numbers we get for online sorting, and then that implies that if we had a good algorithm for packing, we would get a good algorithm for sorting. But I don't have time to explain it. And then this is also an older version of my slides where I also prepared the upper and lower bound for the special case where we do online sorting in an array with exactly the amount of space that we need. And I also don't have time to explain that this is the lower bound and this is the upper bound. Yes, but we show that if we had a C competitive algorithm for strip packing, then we would get a 4C competitive algorithm for online sorting, where we had 2C times n memory cells. And that implies that, so if we had a 4C competitive algorithm for online sorting where gamma is equal to 2C, then we had the trade-off between the competitive ratio and the extra space. So this is a competitive ratio and this is extra space, and we had a result that it should be at least log n over log n. So that means that C is at least the square root of that. So that's where this, that's the lower bound we get. And then I would just like to sketch how the packing algorithm works, because I think it's a very nice open problem if we can make a better packing algorithm, online packing of convex polygons. So the base of the algorithm is that we assume we get polygons of this form, so it's a parallelogram where the width is at most 1 and the height is exactly 1. And then we have a box type tree, so we will always pack our polygons into boxes from of these types here. And so we allocate boxes in the strip, and each box can contain either a piece, and if it does contain a piece, then the area of the piece should be proportional to the box. So that means that the box is well filled with the piece. The box can also contain 1 or 2 smaller boxes. So for instance, here we have a box of this one, of this basic type, and it contains 1 of this and 1 of this. And then when we get a piece, we find the smallest box that contains it. So this one could go into one of this type here. And then we would allocate that and put it in. And now this one is used because it contains a piece. Then we got this one. So you can see that can fill in one of this type. And this one has to be packed into one of this type. So we have to allocate a new one of that, and then one of this type, and then put the piece in there. And now there's room here for one more box from that layer. This one can be packed into this, but this one, there's no room for that here. So therefore we have to again allocate a new basic box and then put that one in, and then the piece can go here. So now both of these can have one more box from that layer. We got this one. It can fit in one of this type. That one has to be packed in one of this type, and that can go here. So we pack it there. This one, I think it can go in here, and then it has to be packed in one of these, and there's no room here, so we had to make a new one here. This one, I think it can go in here, and that has to be packed here, and that one can go here. Oh, it could also go here. Yeah, so this is how the algorithm works. And then we show that that has this yeah, it basically has this this competitive ratio n to the 0.59. Okay, that's everything from me. Then I just want to say that we have open PhD and postdoc positions in my group in Copenhagen, and you can let me know if you want to know more about it. Yes, thank you.
Any questions?
So is the innate hardness also contingent on the fact that you cannot throw away some, both in the strip packing problem and also this online sorting problem, that you cannot throw away any, like say I slightly change the problem that you're allowed, there's another parameter delta, and like delta fraction of the pieces you do not, like you do not cut or you just throw them away.
Yeah, we didn't look at that, but I don't think it works because in our adversarial stream, all the pieces are quite identical.
Okay, so it doesn't matter, even that version.
I don't think it matters, no.
Okay. And so, are there, and like the way you presented it, like this, the trade-off thing, the gamma delta equals omega log n, are there matching algorithms for that?
No. So I think the real bound is probably much higher.
Okay.
Yeah.
Yeah.
No, sorry.
Is there an interesting problem where the input is not adversarial but it comes from a distribution, and you sample some prefix, you look at some prefix, learn the distribution, and then that tells you how to do better on the rest of the input?
Yeah, that's an interesting problem, and I think it's probably very different from this.
Yeah, isn't
Yeah, because it's our lower bound at least is very adversarial. But for the version of online sorting with exactly the right amount of space, we also have a non-adaptive lower bound of the square root n.
Oh, so that square root n lower bound is for even for non-adaptive?
Yes, but that's another paper.
Okay.
That's IISc from this year.
Okay, but if, I mean, like, as was asked, like, distributional information would give you a lot of information in that setting, right? You'll have enough statistic to sort of play, like, say these numbers between 0 and 1 were uniformly distributed, then you'd actually have a very good idea as to where you would place.
Yes, in that IISc paper we also get a better than square root n bound for that version with uniform distribution. Yeah.
So, for oblivious adversary, is it better upper bound? For oblivious adversary?
No, not for packing.
Any more questions?
So for the case where you had the diameter and the total area being delta, right? So what's the motivation for, I mean, having the total area being, is it similar to the diameter, or is there some relation between those two upper bounds?
You could also describe a version with two different parameters. So I think in the potato sack theorem they use one parameter for the total volume and one for the diameter bound.
How do the results change then?
I don't. So we get. So we get that in square packing for a given delta, there is for any algorithm there is a stream of pieces of this area that you cannot pack. And I don't know how it would change if you have two different parent. Then I cannot get my head around it.
Okay, so we can take the remaining questions with the coffee break. Thanks, Peter, once again.
Thank you.
So we'll have the coffee break now and we'll assemble at 11:20. Okay, welcome back. Is it working? Welcome back after the coffee break. Is it working? Hello. Yeah. So welcome back after the coffee break. Our next speaker is Matthew Mary, who is a professor at Université de Montpellier. Matthew did his PhD from École Normale Supérieure and followed it with postdocs from University of Warsaw and then at IDEA's NCBR. He works in approximation algorithms, computational geometry, parameterized complexity, and structural graph theory, to name a few. And today he's going to talk about his work on online piercing set for pseudodisks and rectangles. So over to you, Matthew.
Thank you. So thank you very much for the invitation and the organization of the workshop. I'm very happy to be here, and I want to show you some very recent work I did with my colleagues Marin and William in Montpellier. So this is about, you probably all know the eating set problem, and I want to look at some online version here. So let me describe directly the online version of this problem. So I like to see online algorithm as a game between online algorithm and adversary. So here there is a set of points in the plane. The adversary gives a set of subset of points, and then the algorithm has to choose a point that hits this set. And then the game continues. The adversary gives another set. If this set is not hit by the points of the algorithm, the online algorithm has to make another point inside. Maybe you can take two if you want. And then another set, another point. And at some point, the adversary decides to stop the game. And then we look at the ratio, which is the cost of the algorithm, which is the number of points used by the algorithm, divided by the optimal offline solution, which is the minimum number of points to hit all these sets. So here the ratio is 4. And we say that the algorithm is C competitive if there is no strategy for the adversary to make this ratio worse than C. Okay? So in general, where the sets can be any subset of this set of point P, there is a log n competitive algorithm for this problem, where n is the number of points and m is the length of the sequence. And this bound is almost tight, so meaning that there is a lower bound of log n times log n divided by log n log n. So in general, we cannot do much for this problem. So we can look at some special cases, and relevant cases here are where sets, they are in subsets given by the adversary, they are induced by geometrical shapes, like interval, disk, rectangles, and so on. Okay, and by the way, what is the piercing set? So this is a special case of the eating set problem, where it's the points, they are like this. It's kind of the uniform version where the algorithm can pick any point he wants. But the thing is that we have to put a set of points, otherwise we could make a kind of infinite sequence of nested sets, and that would lead to unbounded competitive ratios. So you have to imagine that this is some kind of pixels of a screen, and the adversary has to choose some shapes that contains at least one pixel. All right, so let's see that we can do. Okay, maybe one comment here is that when we look at geometrical shapes, the number of total shapes is n to a constant. So this log n becomes some O of log n. So basically, this algorithm will always give log n square for geometrical shape. And here there is an example that we can improve to log n for intervals.
N again is the number of points.
N is the number of points of the that we can pick. Okay.
So, what kind of set families alone it are used in the lower bound?
They have to be arbitrarily, I don't remember the construction exactly, but they are complicated sets. So you cannot obtain it by intersecting with geometrical shapes. That's the point.
Still enough small BC dimension, but not geometric shape.
Yeah, they don't have any geometric shape.
Yes.
But it has small BC dimension.
Yes?
That's why you
Okay, that's interesting. All right. What do you mean by small? Okay, maybe I can check.
Opt is still small.
Sorry?
Opt is still small.
Yeah, the goal of the adversary is to produce a solution where the offline solution is small. Actually, he wants the ratio to be as small as possible and the as big as possible, and the online algorithm wants it to be as small as possible. Okay, so let's say I'm the adversary and you are the algorithm. So here is the first interval. What do you do? Yes?
Like, could you go back to the previous slide for a second?
Yes.
So, in this particular algorithm, if the points are on the plane, like P is on the plane, does the lower bound like work even if like the sets have to be like I don't know, somehow connected of some sort?
Yeah, what do you mean by connected? Because it's difficult to define then, no?
You can just have like.
Yeah, I can make a small thing.
Yeah, okay. Yeah, okay. No.
I mean, here when I define it like this, it doesn't. I said that they are in the plane, but it doesn't matter. Just imagine this is a set of points, and it's a hypergraph. Yes. So I give you this interval. What do you do to be a good competitive ratio? So yeah, the good strategy is to pick the middle, because then there is another set that is basically half the length of the interval. If we pick the middle again, basically we will make a sequence of log n intervals. The optimal offline solution is only 1 point, so the ratio is log n. Okay, it's not a proof, but we can prove it's log n. And we can show that we cannot do better for intervals. And intervals, there will be special case of many other geometrical shapes. So what we want in this talk is to, for different type of geometrical shapes, to know what is the real competitive ratio between log n and log n square. Okay. So what is known? There are a few works, and some of the authors are in this room, I guess. So we know about log n for unit disks and half planes. There is a log n bound where this capital N corresponds to any set of points that can be taken in a grid of height n. And this works for squares. So with some students, we generalized these ideas to any fat objects in dimension d, and this ratio was later improved to this ratio, and these authors shown a bound for hypercubes and polygons. So what you can see here I made the assumption on the ground set. So most of the time we need to assume something on the ground set. It's not like a general set of points. Actually, this is a bit more tricky. So these, they correspond to some kind of between piercing and eating set in general. And what you can notice here is that the shapes, they are all fat somehow. And the strategy is some variant of this center algorithm, where we'll always pick the center to kind of, if we want to make a nested sequence of objects, we have to divide the dimension by 2 each time somehow. And one interesting case is what about rectangles, right? It's a simple family of objects that are not fat. And can we get something better than log n in this case, even for the piercing variant? So this is open. And let me maybe explain why this question is difficult. So we believe after our work, and maybe you will realize later, that getting some log n competitive ratio for the problem could make some progress for these two independent open questions that are, can we obtain a constant approximation for minimum eating set? So it's still open. The best is log opt. And for rectangles, the fact is that this is obtained by getting some small epsilon nets, and the bound of the epsilon net is tight for rectangles. So, and we don't really know how to get a constant approximation for eating sets not based on epsilon nets. The other open question that is maybe more general is, so this is the eating set, And this is the independence number. So eating set is always bigger than the independence number, and there's the question, can we bound the other side? So it's conjecture that for a rectangle we can get this bound, that maybe the eating set is at most 2 of the independence number, but still this is open for many years and we still don't know how to answer.
The second one is a purely structural result.
Sorry?
The second one is a purely structural result.
Yes,
It's not
purely
an
combinatorial, yes.
Yeah.
So what we proved, it's not the case for rectangle in general, but we looked at the different type of intersection that can have 2 rectangles. So either one is contained in the other one, or we have side intersections. The other possibility is corner intersections, and the last one is crossing. So it turns out that the difficult case are crossings. So we thought, okay, what if the adversary cannot make any crossing in the sequence? Then we showed that we can get this log n bounds. And the second result, that is a small result, is that if we have only crossings, then we can also get the log n bound. And we let open the question to know if we don't make any assumption, can we get the log n bound? So how do we show that the algorithm for eating set is O of C competitive? So let's say R is the sequence of objects. So here I represented rectangles, but it doesn't have to be rectangles. So I make 2 assumptions on this algorithm. First, if the adversary gives an object that is already it, the algorithm does nothing. So the adversary has no incentives to do that, right? And the second hypothesis is that the algorithm will use a constant number of points for each object. This is kind of verified by all the algorithms I know, but so I assume this is true. Then how do we show that such an algorithm is C competitive? So there are 2 methods. Either we show that the ply is bounded by roughly the same value. So what is the ply is you look at all the points, and for each point you count in how many objects they are contained, and the maximum number of all the points is the ply. So if we manage to show that the ply is at most this constant, then we know that the length of the sequence is at most the optimal solution times the ply, and then we get the approximation, the competitive ratio. So this is rather simple to analyze because the ply is something nice. For instance, for rectangles, this corresponds to rectangles. It's somehow easy to manipulate. A second method is to show that the length of the sequence. So yeah, one thing I didn't say is that this hypothesis implies that we just need to bound the length of the sequence. If we use a constant number of points per object, it's just trying to bound the length of the sequence. So the second method, if we manage to show that the length of the sequence is at most the size of an independent set times this constant C for some independent set, then we get the O of C ratio, because the optimal solution has to be at least bigger than this independent set. Okay? But this is more tricky to analyze because we need to maintain this independent set, and somehow the algorithm has to use this independent set to place its point and so on. So this is a more tricky method. Okay, let's do the second result. So let's prove that we can get log n when we have only crossings in the sequence. So this is rather simple. We pierce the center of the rectangles. So let me show you why it's log n. So we use the first method. So we will show that the ply is bounded by log n. So suppose we have a big clique, meaning we have more than log n rectangles that form a clique in the sequence. So because we have only crossing, the clique has to be like this. If it's long enough, there should be 2 consecutive ones that have roughly the same height, so under a factor of 2, and roughly the same width, so under a factor of 2. And in this situation, both centers are contained in the intersection of the rectangles. So it's a contradiction, right? Because one has to arrive before the other, and we said that the adversary never gives an object that is already hit by a point. Okay, so this cannot happen. so we have only small clicks. All right, so that's it for the second result. I told you it's the easy one. So the difficult one is the first result, where we have no crossings. So we tried center on this, and actually it doesn't work. So there's a no bond of log n square. So this is how it works. So first the adversary gives the big gray rectangle. So we pierce the center, then this rectangle, center again. So there is a series of log n rectangles like this. And then we go to a next layer where we start again with the red one. So we avoid all these points, and again we pierce all the centers. And like this we can make log n layers of log n points, which makes log n square points. And there is one point that touches everyone. So the end solution is only one. Okay, so we need other ideas. So what are the key properties of our algorithm? So let's R be the sequence of objects. So the adversary will never give an object that is already it. Our algorithm uses a constant number of points, including the four corners of each rectangle. So the implication is that we cannot have such type of intersection in the sequence, right? Because one has to arrive before the other. So we will never see this type of intersection. So we will only have to deal with containment and side intersection. So one property of our algorithm is that it will maintain some independent set I, that are always represented by the blue color, such that the length of the sequence is at most the size of I times log n. So this implies that the algorithm is log n competitive if we manage to do so. And another thing that we want is that the algorithm for each rectangle that is not in the independent set, so the black one, it never contains a corner of a blue rectangle, of a rectangle in the independent set. Okay? I will explain why it's a useful property. But the thing is that we cannot really ensure this. So if that happens, what we will do is that we will trash this rectangle. We will forget this rectangle. We will consider that it never happened. It never appears in the sequence. And so the algorithm will maintain some partition of the sequence. So there will be this independent set, these rectangles that were trashed, and the rest of rectangles that are the active rectangles. And the goal will be to show that this set is at most as this bound, so we want to bound these two sets by this. Okay? So why do I make this assumption here? Because we can get a nice planarly structure of the pair, the independent set and the active rectangles. So here we create a vertex for each rectangle of the independent set, for each blue rectangle, and if two rectangles there is a rectangle that intersect both of them, we will put an edge in this graph. Okay. So the question is, why do we get a planar graph? So the answer is because a black rectangle, if we make this assumption, never intersect more than two blue rectangles. Okay, so imagine it. This black rectangle is intersecting these two blue guys. If there is a third intersection, it must be either like this, but we have a crossing. We said it's forbidden. Or this rectangle R prime prime should have its two corners inside the black rectangle. And we said this doesn't happen because we forget some rectangles. So this planar structure will be very useful later. So here we can see that if we have that, we can partition the black rectangles into, so the one that touch exactly one person, so we call it X of R1, that are the one that touch exactly R1, and the one that touch exactly two rectangles that correspond to edges of this graph. So here it's represented by the red color. So I called the green one the loop rectangles, and the red one the edge rectangles. Okay, so how do we maintain the fact that active rectangles, they are much, the bound is the size of I times log n. So first, we will make sure that I remains locally maximal. So if it's not the case, we will do a swap. So we will change I. So a first type of swap is if there is a rectangle that is independent from I, we just add this guy in I. Okay. So this ensures that the sets X, they partition the active rectangles. So the second type of swap is if we have a blue guy that is incident, there are two black guys that touch this guy and they are independent, then we swap. So we will trash the blue one and we will add the two black guy in the independent set. Okay? And the third, so this ensures that when there is no swap, X, the loop rectangles, they form a clique. Then the third type of swap is if we have two blue rectangles in the independent set and there are three active rectangles that are independent and touch these two rectangles, then we swap again. So here we trash these two blue rectangles and we add the three in the middle to the independent set. And this implies that when we have an edge between two rectangles, like if I show this again, here we can have only two rectangles. We cannot have three, otherwise we could make a swap. So in an edge, we have at most two clicks. So this will be useful later. So we will try to make sure that clicks, they have size log n inside the active rectangles, some kind of equivalent of having a ply bounded by log n, but this is only true for the active rectangles. So I will explain how to do this later. If we add the fact that the instance is planar, then we get the bound on A, because for each blue rectangle, the loop rectangles, they form a clique of size log n, at most one clique. And for each edge, so there is at most 3 times the number of edges, at most 3 times the number of vertices. And for each edge, we have at most 2 cliques of size log n. So at the end, we get this bound. If we manage to maintain these cliques of size at most log n. So how do we do that? So for this, we will use some what we call piercing invariants. So let me show you an example of how the algorithm will work. So first, the adversary gives this rectangle. We will pierce the 4 corners plus the center. There is a swap, so we add this guy in the independent set. Then the other rectangles goes inside. We also pierce the center. And here there's another rectangle that comes. Here, additionally to pierce the center, we will pierce the center of the intersection with the other one. So this will make sure that the area of the intersection of the clique inside will decrease by 2 each time. So we will have at most a clique of size log n inside the rectangles. So the other type of piercing invariant that we have is for the side intersection. So imagine we have a rectangle that arrives on the side like this. Then we will pierce the middle of the intersection with the side. This guarantees that if we have another sequence of rectangles that arrive like this, we have a size at most log n. This is like the interval case, right? So if we maintain this piercing invariance, we guarantee that the cliques, they will have size log n. So same happen if we have a rectangle that touches 2 blue rectangles. Then we pierce the middle of the intersection on both sides. So this is an example. So here something happened. Look, there is this rectangle that just arrived. And so now they are independent. Both of them, they touch the blue one. So we can do a swap to increase the size of I. So that's what we do. So we put this guy in the trash. And we will also remember that we want to avoid, now that they are blue, we want to avoid other rectangle to contain corner of them, to maintain the nice structure, nice planar structure. So we put these guys all in the trash. So why is it okay? Remember that we need to keep a small trash. It's because each time the independent set is growing by 1, we are allowed to trash log n rectangles. So, and here it's a constant number of clicks, so if we maintain the fact that they have size log n, this is okay to do that. So here we managed to maintain the structure we want. Look, here there is another swap now, because this guy, because it was an edge rectangle between two blue, and now it becomes a loop rectangle of the blue one on the right. So now we have again an independent set of size 2, and we can swap with this one. So we swap, we clean the instance, and here we get this instance. And we continue. Okay, so this is the invariance that we need to maintain in order to guarantee that clicks, they remain small. So piercing the center of the intersection when we have the containment intersection, and piercing the middle of the sides if we have the side intersections. So can we really maintain this invariance after a swap? So look at this example. Here, there is this green rectangle that arrives, and this green rectangle that arrives. So we do a swap, but now this guy is in the independent set, but here there is no point, here there is no point, and also here there is no point. So there is a problem. So what can we do? So the first idea is that these guys, we can trash them, because we know it's a click, and it has size log n. So because the independent set has increased in size, we are allowed to trash log n rectangles, so we'll do that. So for this one, it's okay. But the problem is that here we may have a lot of rectangles, so we cannot trash them without maintaining a small cache. So the idea is just, okay, we will put new points to make sure that our piercing invariant is satisfied. But there's a problem, because we wanted to make sure that we maintain a constant number of points per rectangle. And it turns out that there are examples where rectangles R could be repierced many times, which is a problem, and I don't want to detail the example. But the magic trick here to make sure that a rectangle is not repierced 2 times is that when we have some so when we have these edge rectangles, we will trash some of them, and we will put them in a special trash. So what is the criteria to put them in the trash? It's just when this guy enters in the independent set, we will look at the other side, and if the edge contains one rectangle that was repierced from the other side, then we just discard these rectangles. So we just put them in the trash. This one, they stay, because they were not repierced from the other side, and in that case we add some new points. And it turns out that this works, so what we need to check is that a rectangle is repierced only a constant number of times, and this special trash has size, the size of I times log n. So I'm not sure if I have the time to go over the details, but here in example where it's repierced at most 3 times, so basically this rectangle R will be repierced by these 2 guys that will enter the independent set in a sequence. So we can prove that we cannot do more than this. So I assume that this is okay. Now how do we do that? There is a nice trick. The thing is that we cannot bound it locally, so we have to have a global analysis. So the analysis is just based on, we will build some kind of, some bipartite graph, where on one side we have the rectangles that entered inside the independent set, and on the other side we have the rectangles that left the independent set, and we put an edge between 2 rectangles if at the moment where this guy was removed from the independent set, the corresponding edge was put in the special trash. Okay? So it turns out that the number of vertices is O of the size of the independent set, and the number of edges trashed, the number of rectangle trashed each time per edge is log n, because they are formed by a constant of clip. So we just need to bound the number of edges. And it turns out that if we have a lot of edges, there must be a K33 induced in this bipartite graph, and we can figure out that there is also a K33 in the original graph of the instance, which is a contradiction with the planarity. So we have these two things. So here is the full algorithm. I don't think I have the time to detail again everything, but I would be happy to talk with you if you are interested. So the conclusion is that we gave a log n competitive algorithm for online piercing of rectangles if no pair of rectangles of the sequence is allowed to cross. So a nice byproduct is that we proved the conjecture about the gap between the independent set and the heating set for this case, and we got a constant 11. So it's actually quite simple, so I believe that this was known before and not worth publication, but this is kind of nice byproduct of our result. And it's just based on the planar structure of the I and R. So maybe small open questions. So that would be great to generalize to any set of points in the plane and not just the grids. Actually, it's quite open for many things. I think it's still open for squares and disk, but I'm not sure because there were some recent papers on archive. So maybe not, maybe yes, I don't know. And that would be great to get some lower bounds for geometrical objects. And yeah, of course, generalize to arbitrary rectangles for the piercing at least. All right, thank you, that's it.
So you had the lower bound of log square n for geometric piercing. What is preventing you from extending that to geometric fitting set?
Sorry again?
You had the lower bound of log square for the geometric piercing.
So this is for the center algorithm. The lower bound of log n square.
Just for that one algorithm?
Yes, it was just to show that this center algorithm doesn't work. That was just because usually center was used, some variant of center was used for all the other cases, but for this case it doesn't work. Yeah.
So, if I understood correctly, to extend this algorithm to the hitting case where you have points anywhere, so the main bottleneck is that in those common intersections you might not have a point, right? And I was just wondering if there is any structural property that in such cases can you say something that like is there an instance optimal better argument? Like
you mean to generalize for this?
Yeah.
So to be honest, I haven't thought a lot about this problem. Maybe I thought maximum half an hour on it. So it's open, and that could be one thing to do in this workshop actually.
I see.
So I would be happy to discuss with you if you have any ideas.
Sure. I mean, because it feels like if you don't really have a point in a clique, then instance optimally it's also worse, right?
Yes.
And what would opt do?
Yes. But then the lower bound with the size of I would, I don't know if that would still work.
Right.
I don't know.
So what is known about the set cover variant of this? So you want to cover points with let's say
Yeah, so this was studied by Arindam, Andreas, and other people. So I'm not the expert. Maybe maybe Arindam, you can answer. But there are some. Wait, what is the result? You get some log n bound for any set of points. That's the
any set subset, but for unweighted case, and then unweighted set.
Unweighted. So for rectangles.
Squares,
So for squares. So there is a log n bound for squares, where for the eating set problem.
For set cover.
For set cover. Yeah, for set cover. Sorry. I meant not the where there is the grid. It can be any set of n points. Or n sets. I don't.
Okay. Any more questions? Let's hand once again.
Oh, thank you.
Malin Rao. So Malin is currently a professor at the Chalmers University of Technology. Prior to this, she did her PhD from the University of Kiel and then held postdoc positions at Grenoble and University of Hamburg. Her research focuses on approximation algorithms for packing and scheduling problems. And I would like to thank Malin to be here because I guess your visa got approved at the last minute. So a special thanks for being here today. So today she is going to talk on her recent work on a tight 3/2 plus epsilon approximation for the demand strip packing problem. So over to you.
Thank you very much. Do you hear me well? Or should I?
Yes, yes.
Yeah. Okay. Yeah, thank you very much for the kind invitation and for the organization of this workshop. I'm really happy to be here because it was really not clear until last Friday. So yeah, I made it and I'm happy about it. Yeah, the work I'm presenting was accepted at Zoda this next year. And yeah, I'm really happy about that as well. And I'm also happy that Andy already did a lot of introduction to packing problems. So thank you for that. Also, you got delivered a lot of motivations for it, so I don't need to do. You have a question? Yeah, okay. Should I?
The mic you can keep it in the center.
No, it's not on.
Oh, it's not on. Okay. Yeah, no, it's fine.
Thank you.
That's fine.
Can you hear me better now? Thank you. Yes. So the problem we study is the following. We have given a set of jobs, and they have a processing time, and they require some energy. And we want to schedule all these jobs until a certain deadline, D. And we want to minimize the maximum energy demand the jobs have at some point. And yeah. Why do we want to minimize the energy demand? This can be important if you think about your energy grid and you don't want to use too much energy in that grid at the same time, so you want to minimize the peak. And this has a lot of similarities to strip packing because we can interpret this time frame as the width of the strip, and we want to minimize the packing height. But for strip packing, we have to pack these items as rectangles, while we are here allowed to cut these items in some sense, because we're only interested in the sum of energy gases. Yes. So the strip packing would look like this. And this is actually a well-known example from before. The example usually doesn't use this job here, but like this it's easier to see that this, the first one was so optimal.
So you can only cut vertically and move vertically? Yes,
because you have to schedule the jobs in one go, so you cannot interrupt the jobs and start them again, and you just sum the energy at the time, so which is why you can represent it in different ways. You can either cut them like this, and all parts of the jobs have to start at the same time, or you cut them vertically and shift this part to the top. That's equivalent. It's just how to represent it.
How does it connect to make span?
To make span, it's different actually. So for make span, we can look at it like this. We have a fixed number of machines,
right,
and we want to minimize the deadline. And it looks very similar, but it's different because if you look at pseudo-polynomial time, for make span minimization, it is known that there's a pseudo-polynomial 1 plus epsilon approximation, while for this problem we cannot get below 5/4. It looks very similar, but it's different.
And the output of the algorithm will be just the start times for every job.
Yes, it
And
will
that
just
completely specifies.
Yes.
Okay.
Exactly. Yes. So what was known before? Before there was at least a 2.7 approximation, which is a very classical result. Then, as these jobs can be interpreted as rectangles, we always can use the Steinberg algorithm for strip packing to solve the problem as well. Because the Steinberg algorithm only considers the area of the items and gives a result with regard to the area. And then, in 2021, two groups found the same result, 5/3 plus epsilon approximation. But the nice thing about this is that the approaches to find this 5/3 plus epsilon approximation were completely different. And what we did now was combine these two approaches to one to find the 3/2, which is really nice, I think. Because, yeah, like two different approaches leading to the optimum in the end, which is, yeah, I haven't seen that often yet, but I'm not as long in science. Okay. So yes, we find 3/2 plus epsilon approximation. And how these two approaches I mentioned before work, basically, we can see here already. So what for this kind of packing is always interesting is to look at the items which have a height which is taller than 1/2 of the height of the packing, of the optimal packing. Because if we want to find a 3/2 approximation, we know we cannot stack these items on top of each other in our solution. And we define two kinds of packing. A lambda forgiving packing, which says we can rearrange the optimal packing in a way that we can introduce one more item which has height of optimum and a small width. And then we can take this item and squeeze it somewhere inside this packing by rearranging this original packing. And the other one is an optimal neat packing, which means that we sort all the items which have a height which is taller than 1/2 in decreasing order of their height and place the other items somewhere in between. So both approaches take the optimal solution and rearrange them somehow. And one of the papers I previously mentioned, we ordered them in this way, similar to this way, just a 5/3 approximation. What was it? Like the other approximation ratio as height, and here as well. The other algorithm introduced also this kind of item, but the height of the rearranged packing was a little bit larger. Yes. And what we do now, if we know, given any optimal packing, we can rearrange it that we either can introduce this new item or sort the tall items. Then we can either directly use the algorithm from before, or we slightly modify the other algorithm and use that to solve this. And the overall algorithm then is we use a binary search algorithm and try for each approach if we can find a packing which is lambda forgiving or epsilon neat. And if yes, we decrease the search direction, and if not, we have to search for a larger direction. So yeah. just combining these two. And yes. The general idea is to consider different cases, how an optimal packing can look like. This is one example. And then see that we can somehow shift items or blocks in this packing such that it looks like this, for example, and has a height of at most 3/2, and we can either introduce this item or sort that. And to do this rearranging, we use two crucial techniques. This one here I have not seen before. I don't claim it's new, but I have not seen it before. And it's a so-called stretching, where we have a set of, we have an area where we have a lot of tall items, and we have items which are completely contained in this area, which are here in green, and we want to take them out and put them into a container which has a height of at most 1/2 oct and a slightly larger width than this area before. This allows us to sort the items inside here, squeeze them together, and get some free area where we can place an extra item, for example. And we call this stretching because what is happening, if we look at one of these areas where no tall item is placed, like this, we take out all the items which are completely contained in this segment, remove them, and for the items which overlap one of these lines, we shift all the items which start up after this point A exactly this width to the right. So we stretch the packing by a bit, by the width of this segment, and so find the packing which has the height of at most 1/2, because these items have height at least 1/2, so this part has height at most 1/2. Yes, and the items from here will also contribute to the part we need extract. So this part here consists for one for the stretching, and because we need to place these items. Yes. And the second is squeezing. This has been used by one of the two papers. And it didn't have that name, but it has been used. And there the idea is basically we take an optimal or a packing and consider all these items here and try to shift them as far as possible to the left. And as these items only have a height of 1/2, it's always possible to shift the items such that we keep a profile which is at least 1 plus some epsilon, which means that in the end we should have some free area where we can place an extra item which has a height of 1/2. And the width of this item depends on epsilon again. And this allows us to squeeze in additional items, and it allows us also to not consider, when we repack our items in this way, not consider items that are very thin. We just can forget about them because we always can place them in later. Yes. Yes. And what we mainly do, because the algorithms are already known, is mainly showing this structure result such that these packings can be rearranged to be neat or forgiving. And we do this via a case analysis, and I don't want to bore you too long with this. I just give a small overview what we do. The first example you have already seen. this is a technical one where we need the stretching. Here we have a segment, and we have many tall items in between, but there is a free area or a free width of tall item which has a width between lambda d and 2 lambda d. And in this case, the rearrangement looks like this, and we can squeeze in this extra item. Therefore, we add the extra item. If the optimum solution has not this case, it has one of the following. Either there's no tall item, then we are already neat because all the tall items that exist are sorted. Okay. So then the next case is if all the tall items have a very large width. In this case, we have a different packing structure where I don't want to go into detail. And then the last case is there is a gap between two tall items which has a width of at least lambda d. This then has to exist because we are not in the first case. We have tall items, and yes, the tall items do not span everything. So we have to have a width of at least lambda d between two tall items. And this again splits into a lot of subcases. We have a gap which is between lambda d and 1/2 minus 3 lambda d, so almost 1/2. Looks like this. Then we have a gap which is at least 1/2 minus 3 lambda. And there we have one case if we have one gap, and another case if we have two gaps. And then it looks like this. Yes. And this already concludes my talk. So the main idea was to use the stretching and squeezing to find rearrangement of the optimal solutions in all the cases which occur. I don't want to go too much into detail. And then using the existing algorithms to find the packing for these, or schedule for these items. Yes, and I somehow hope that this stretching can be used in other problems. For example, hopefully the strip packing, because strip packing is still open. We don't have the 3/2 plus epsilon approximation yet, which might be possible or not. And so the stretching should, for example, transfer, but the squeezing does not, because the squeezing really assumes that we can split the items and shift them down and squeeze something in. So that cannot be used, but maybe other things. Thank you very much.
Thanks, Colin. Questions?
The lower bound of 3/2, does it come from bin packing?
Yes.
In that case, is it asymptotic?
It's partition what is laying below, so, which is also which gives bin packing the lower bound.
So is this lower bound of 3/2 asymptotic or absolute?
It's absolute. So asymptotic depending on how you define it. So there are 1 plus epsilon plus H max approximations for strip packing as well.
Thanks.
Can you do better than 3/2 in pseudo polynomial time?
Yes, for this problem, yes, and that's also already solved. There you can find, I'm so bad with fractions, 5/4 plus epsilon, and 5/4 is also the lower bound. This transfers from strip packing really nicely.
I see, yeah, good, thanks.
Any more questions, anyone? Okay, so let's thank Malin once again. Okay, so we'll break for lunch now and we'll meet at 2.
Oh yeah. And the advantage was that there was no traffic. Everything's easy and it was like a oh, that's good.
Yeah, what is it called? French New? Yeah.